Lesson 2.5 takes the parent functions from 2.4 and translates them all over the graph. We'll use translations based on changes in the parent function equations. Let f of x equal absolute value of x. We'll start with that parent function. Show the graphs of g and h as follows. So the parent function is already given to us over on the right. I'm going to write f of x equals the absolute value of x. To show how that graph happens, let's make a table. If I plug in 0, the absolute value of 0 is 0. If we plug in 1, the absolute value is 1. But when we plug in -1, the absolute value of -1 is 1. If you plug in 2, the absolute value is 2. If you plug in -2, again, absolute value is positive. So that's where all of these points are coming from, on the right side and over here on the left side. Absolute value is always positive, so notice all of our outputs are above the x-axis. But watch what happens when we change the equation. Let's see how that will change the shape of our graph. For g of x down below, it says g of x equals f of x plus 2. And if f of x is the absolute value, then we would say g of x is the absolute value of x plus 2. So now when we make our table and we plug in 0, the absolute value of 0 is still 0, but when you add 2 to that value, it moves it up 2. If I go 1 to the right, the absolute value of 1 is 1, but if you add 2, it goes up to 3. -1, absolute value would be 1, plus 2 is 3. 2, the absolute value stays 2, plus 2 is 4. And -2, absolute value would still be 2, plus 2 is also 4. On the graph, 0, 2, 1, 3, oops, get that a little darker there, -1, 3, 2, 4, -2, 4. And we could continue on. This graph moved up from the parent function. So to describe it in words, how far up did it translate? It moved up 2 units from the original set of values. So we'll say moves up 2 units. All right, let's try h of x. Same idea, it's still related to the parent function, but now h of x is f of x minus 3. And since f of x is that absolute value, we do absolute value of x minus 3. Can you already predict what's going to happen here? Let's check. Since the minus 3 is after the absolute value, all of our numbers on the left side are going to stay the same. The absolute value of 0 is 0, but minus 3 would move it down 3. 1 to the right, absolute value of 1 is 1, minus 3 is -2. -1, absolute value is 1, minus 3 stays -2. 2, absolute value would be 2 minus 3 is -1, and -2 would give us -1. So now we have negative outputs, but only because there's that minus 3 after. So 0 minus 3 puts us down here. 1, -2, -1, -2, 2, -1, -2, -1. We can keep going. I'm just going to go up and over 1 each time in both directions. If I connect my dots all the way to the edge of my graph on each side, notice the shape generally stays the same. We've just moved it up or down. I'm just going to move that over here just a little bit. To describe this in words, we would say moves down 3 units from the original parent function. Anything that is added or subtracted just shifts the graph vertically, either up or down. Let's try another round of transformations. Let f of x equal absolute value of x again, so you can see our graph on the right. Now show the graphs of p and r as follows. P of x equals f of x plus 2. So now this is different. If x plus 2 is in the parentheses, then p of x is going to be the absolute value of x plus 2. Whatever's in the parentheses is what goes in that absolute value kind of location. From quadratics, we've talked about this before. This means we're going to move everything left 2. And if you're thinking to yourself, why left? Because in the parenthesis with x, it always goes in the opposite direction. So think about that. What this means is instead of starting at 0, I'm going to move over 2 to the left, so I'm going to start at -2 because I'm moving 2 to the left. And if you plug in -2 to the absolute value, -2 plus 2 is 0, and the absolute value is 0. And then I'm just going to go on either side of -2. I'll go to -1. -1 plus 2 is +1. Absolute value stays 1. But if I go to the other side of -2, that would be -3. -3 plus 2 is -1, but the absolute value is 1. I'm going to keep going. I'm going to go to 2 on each side. So instead of -2 and then -1, I'll go to 0. 0 plus 2 is 2. Absolute value is still 2. And then on the other side of -3, I'll go to -4. -4 plus 2 is -2, but its absolute value is positive. Let's plot these points and see if it did actually move to the left. So if I go -2, 0, and then -1 up 1, -3 up 1, 0 up 2, -4 also up 2. If I connect the graph all the way in both directions, over to the right and then over here to the left, notice from the original function, the green graph did in fact move left 2 units. All right, let's try the other one. R of x equals f of x minus 3 on the inside. Again, this means the absolute value is x minus 3 on the inside. Since it's subtraction, this will now actually move in the opposite direction. It'll move right 3 units. And because it moves 3 units to the right, instead of starting at 0, I'm going to start at 3. And I do that because when I plug it into the absolute value, 3 minus 3 is 0. It's kind of that turning point of the absolute value graph. And the absolute value of 0 is 0. Since 3 is kind of our pivot point, I'm going to go on each side of 3. I'll start at 4. 4 minus 3 on the absolute value is 1, and the absolute value of that is 1. And then I'll go to the other side of 3, I'll go to 2. 2 minus 3 is -1, but again, its absolute value is 1. If I go to the other side of 4, I'll go to 5. 5 minus 3 is 2, absolute value is 2. And if I go to the other side of 2, I'll go to 1. 1 minus 3 is -2, but again, absolute value is 2. If we plot these points, 3, 0, 4, 1, 2, 1, you can already see that shape starting to form. 5, 2, and 1, 2. Again, connect these from that pivot point. I'll go to the right, and then all the way up on the left-hand side, whoops, as best you can, draw that in there. So it may not show it going all the way in that V shape like the parent function, but it's keeping that same shape. And this graph does in fact move right 3 units. So if the adding and subtracting is on the inside of the parentheses, this is horizontal, and it moves in the opposite direction. Now let's try some work with negative coefficients. And we're going to start with a different graph this time. Now we have f of x equals the square root function, or the square root of x. So what I'll do over on the right is we'll write out just a quick table for that parent function, and then we're going to look at g of x, h of x, and k of x. So if you have 3 colors, now would be a great time to have those for this part of the lesson. If we start off with our parent function, f of x equals the square root of x, we know that this is an even root, so that the domain has to be greater than or equal to 0. We've already talked about this in chapter 2. In our table, if we start with 0, the absolute value of 0, or excuse me, absolute value, the square root of 0 is 0. And there's that point over here on the right. The square root of 1 is 1. This graph is a little bit off. I'm not quite sure why. So that should be at 1. Just put a big dot there. The next perfect square goes all the way to 4. And that would be 2. The square root of 4 is 2. If you kept going, the next perfect square would be 9. And that would be 3 if that fit on our graph. And then you could go to 16, 25. Any other numbers would just have a decimal output. And that's fine too. So notice the original parent function goes over here to the, and I'm just making a big mess here, to the right. I'm going to redraw that whole thing. What a mess. All right, well, you guys can actually see it even too. So we'll just kind of make that darker right there. As it goes to the right, notice it doesn't go to the left because we can't plug in negative values for x. But let's see what happens when we change up the equation just a little bit. For g of x equals negative square root of x, notice they've already plugged in the parent function, we just have a negative out in front. So let's see what that negative does to our inputs. Notice nothing changes with x, so we can use the same inputs we did last time. 0, 1, 4, and 9. The square root of 0 is 0, and then the negative on the outside, negative times 0, stays 0. So our first point doesn't change at all. If we plug in 1, the square root of 1 is 1, but the negative out in front now makes that negative 1. 4, the square root of 4 is 2, but that negative out in front will make it negative 2. And 9, the square root of 9 is 3, but the negative out in front changes it to negative 3. So we still have our 0, 0. 1 now drops down to negative 1. 4 would drop down to negative 2. And if we try to make this curve happen, notice it just kind of curves down below instead of up above. So when there's a negative on the outside, this will reflect over the x-axis. That's how you would describe the transformation. All right, let's try h of x. H of x has the negative on the inside, so now our x values are going to change. So if we make a table, whoops, and I don't know where that line was coming from. Let's try that again. If we make a table of values, we have to be careful what we plug in for x. We can't plug in 1, 4, and 9 because that would make 1, negative 1 on the inside. So we have to actually change these signs in order for the inside of the square root to be positive. 0 is fine, oddly enough, because 0 doesn't change the plus or minus, so that'll stay 0. But instead of plugging in positive 1, we need to plug in negative 1. And that way, if we call it negative x, that would be a double negative 1. So it'd be negative, negative 1. And that cancels to be the square root of 1, which is 1. Instead of 4, we have to plug in negative 4, and then the negative on the inside with x cancels out, and you'd have the square root of 4, which is 2. And even if we went all the way over to negative 9, the square root of negative negative 9 would be square root of 9, which is 3. So our start point stays the same, 0, 0. But now we have negative 1, 1. That should say equals 1, not negative 1. Negative 1, 1. We have negative 4, 2 over here on the left. And then if we all went all the way over to negative 9, we'd only go up 3. So notice this graph goes in the opposite direction. So this graph reflected over the y-axis. Make sure to write that down. Reflects over the y-axis. If the negative is on the outside of the parent function, it reflects over the x-axis. However, if it's on the inside, we have to be really careful how we create our table, and it reflects over the y-axis. Now look at k of x. K of x has a double thing happening here. Not only is there a negative on the outside, but there's x plus 2 as the radicand. This changes our domain. So now we have to think about, oh boy, if there's something with a domain rule, we have to worry about that as well as the transformation. Remember the rule for the radicand. Whatever's on the inside has to be greater than or equal to 0. So if I move 2 over to get x by itself so that we know what to plug in, x has to be greater than or equal to negative 2. So that's going to move the graph 2 units to the left, which is the opposite rule with x, but it's on the inside with x, just like it was up above with that absolute value. Oh, so much to remember, you guys. All right, so on the inside for the table, instead of starting at 0, we're going to start with negative 2. Plug it into the formula up above. If we plug it in right here for x, negative 2 plus 2 is 0, square root of 0 is 0, and even with that negative out in front, it stays 0. So that's not so bad. If I go 1 to the right, go to negative 1, because that's greater than or equal to 2. Negative 1 plus 2 is positive 1. The square root of 1 is 1. However, that negative out in front makes our final answer negative 1. Oh, this is a lot to remember. The next perfect square would technically be 4 on the inside. So what would x have to equal? If we say x is 2, 2 plus 2 is 4 on the inside. Square root of 4 is 2. And then that negative out in front makes it negative 2. The next perfect square would be 9, but we'd have to add 7 to the inside for x. 7 plus 2 is 9. Square root of 9 is 3. But then that negative would make it negative 3. I think we've got enough points to plot here. Negative 2, 0. Negative 1, negative 1. 2 down to negative 2. So you can see the graph kind of does one of these over here. So not only did it move left 2, but it did another thing. So we have to describe both parts. Moves left 2 units and reflected over the x-axis. So it did double duty. All the graphs on this page are examples of rigid transformations. That means the basic shape of the graph stays the same. It may move up and down or left and right. It could even reflect over the x or y axis, but we have not changed the actual shape of the graph. When we look at non-rigid transformations, we'll look at stretching and compressing, which will slightly distort or change the shape of the parent function.